Hi, everyone. I'm Ejtima from from Tencent Xiong Lab and from China. So thank you for your listening to this talk. In this talk, I'm gonna talk about the how I doing the massive scale USB driver fuzzing and how I achieve this fuzzing without any hardware. So here's the oops. Yeah. Here is the just a brief introduction of my experience, and I'm security researcher from Tencent Xiong Lab, and I'm used to doing chemistry, but now just trying to do some coding and hacking, and most of my work is focused on the hardware hacking and like the firmware reverse engineering and the software hacking and console hacking, and I also do some geek stuff like the RFID and the lockpicking and something like that. So let's go to the agenda. I divide this talk into thank you. I divide this talk into four parts, and in the first part, I'm gonna talk about some basic, give some brief introduction of the USB protocol and the drivers basics, and then I'm gonna talk about how I created the hardware and to trigger the USB driver loading and to make it work. And then I'm gonna talk about how I implement the fuzzing, and then some results show and some demos. Just it didn't work. Oops. Okay. So yep. This one. Okay. Thank you. So the first, I'm gonna talk about the USB and drivers, and as you know, I won't. I think you guys quite familiar with the USB and is very often used in the normal life. So I won't dig into too much into the details of USB technology. Just summarize some features of the USB bus, and mostly we often use USB to do some data transfer, and also it's include a lot of the device classes like the HDI USB device or the camera and some and printers. So and in the latest version of the USB protocols is also support the quick charge, and you can just charge your phone or your laptop with a very quick, very quickly, and you can just use it to do it. And one of the characteristics of the USB I have to emphasize is determined by two IDs, and one ID is VID, and we call it is vendor ID, and the other is PID, is product ID, and the VID is assigned by the USB forum, and the PID was just assigned by each vendors, and on the right column, you can just see some summarize the previous research on the USB and the first project I have to mention is the Visual USB Fuzzing framework, and this was announced on I think is 2015, the Black Hat USA, and the author trying to do the visualize the USB device and to do some massive fuzzing on on Linux-like operating system, and this research just inspired me to do this research. And the second is most famous USB research is about the battery USB. And you can just use the device to simulate as a keyboard or a mouse to just do some malicious work on the victim PC. And also some guys also do some a little bit research on the USB protocol fuzzing, and they use phase sensor to do the man-in-the-middle USB protocol fuzzing, and to discover some vulnerabilities, but it's not in large scale because they have to use 2 phase sensors to do this fuzzing, and it's really time-consuming because the microcontroller on the phase sensor is not really high. And also the most famous USB bugs on the console hacking is the PS3 USB jailbreak, and there is a bug when they process the USB descriptors, and then they use these bugs to achieve the code execution in the PS3. And the most latest news on the USB research is the Nintendo Switch jailbreak, and is a USB stack when they process some command, and is cause the buffer overflow, and they can just gain the very low level code execution, and to just bypass any security features inside the console. So, and then we go to see some basic of the Windows drivers. And the first keyword I have to mention is the frameworks. And as you know, if you have the experience on developing the Windows drivers, and you might familiar with these words, and in the very legacy age, and Windows use the VXD drivers on the Windows 98, and then they evolve into the Windows driver model, and is WDM framework. And now in Windows 7, and they use the Windows WDF and the Windows driver framework, and to develop the drivers. And the Windows drivers has a lot of types, and like the audio video streams, and some netcast drivers, and some filters, and some ports. There's quite a lot of types, and they also and the third keyword about the Windows drivers is they have developed by both Windows, both Microsoft and third-party developers. And then you have there are a lot of bugs in different drivers. And if you work with the Pontoon computation, you may quite familiar with the Win32K drivers, and there's a lot of bugs, and to escape the sandbox of the browsers, and there's quite a lot of security research focus on the antivirus drivers to gain much more privilege on the Windows. And also, if you are a beginner of the trying to discover the driver bugs, and you may first focus on the I/O control fuzzing. And so there's a lot of bugs in the Windows driver. So here we come the ideas of our research. So imagine if we plug a USB device into your host PC, what will happen? And the first level is the USB host controller drivers, and the USB hub driver will start a process called the enumeration. And the enumeration means they trying to collect some basic information from the USB device, and to determine and to configure it to make it work. And after that, these drivers will try to load some class drivers depending on the information they collected before. And if the USB device is a massive storage, like the flash drive, it will try to load the USB store system drivers and then do some further initialization. And after that, the system gonna to use some device-specific drivers. So, and then let it run. So if we just simplify this progress, you will see this progress is we plug one device and gain the code execution in the kernel mode. So if we can find some bugs during this process, that would be give us to control this code execution in the kernel mode and gain the kernel privilege. So here's the attack scenario. So on the left side is your computer, and on the right side is the server. So when you're trying to plug your USB device into the host PC, it's trying to communicate with the remote server to search the drivers for this device. Once the drivers was found in the remote server, it will deliver the drivers into the PC. And after PC get these drivers, it will try to unpack the driver file, the cat file, and then verify the signature of each binaries, and then install the drivers into the driver store, and then load the driver into the kernel mode, and call the entry point of the driver, and then initial some IRP message inside the kernel mode, and call the corresponding IRP handler to process it. So as you can see, we plug a USB device. We triggered two kind of code execution. The first is the entry point code execution, and the other is corresponding IRP processor, handler execution. So what we can do is to trying to find the bugs of these two processes. And here is the goal. And we're trying to find the bugs that was automatically installed during you plugging your USB. And then we trying to exploit every code execution process and to see if any bugs during the code execution. And additionally, we're trying to find the IO control code bugs, and we will initializing error control code fuzzing during when the driver is successfully loaded. And the second goal we want to just achieve this tag is plugged upon. Means we trying to plug a craft USB device and then gain the code execution and then do whatever we want. And later, I just give a demo of this plug-to-pong attack. And so the first question came up to us is where to get the target, and where and how to get the target. And let's recall the process and how Windows to grab the corresponding USB drivers. And obviously, the driver is stored on the Windows Update drivers and servers, and when your USB was plugged into the PC and is trying to search trying to submit the information into the server, and the server will return back a result whether they have the driver or not. And the information they submit to the server is the VID and PID we mentioned before. And the protocol is also documented, and so we the best choice for us is to create a fake client with some Python and just a little bit reverse engineering, so we can enumerate each combination of the VID and the PID. So here comes the result, and we do quite a lot of work on these 4 platform of Windows and get all the results, and it's totally about 4,000 drivers we have to analyze and fuzz. So, but before we go ahead, we have to just start a bit and to do some calculation on the combination of the VID and PSD. If you do some math on it, you will find the combination numbers is really huge. We cannot to finish such enumeration on this combination in a reasonable time. So the solution is we found a link. And the link is provided by Microsoft. And we can use this link to, first we search about the VID. And we can just, we can make this number very, very small. And then we got, we got about just 1% of the VIDs, and then we use the VID and do the combination to each PIDs, and then we got all the results. So after we got the target, and we have to find a way to trigger the USB driver loading. So in this progress, the essential element is to create the hardware. So if we recall what consists of the USB device we found is consistent of 3 parts. And the first part is a USB socket, as obviously, and the second part is a microcontroller inside the device, and then and with it is corresponding the firmware. And all the information and the function was embedded into the firmware and running by the microcontroller. And when the device, when your USB host trying to gather some information of the USB device, the microcontroller just do some calculation and send the data back. So, but we cannot prepare the every USB device for each USB drivers is impossible and costly. So we have to find a way to make it, and we do the emulation. So let's see how we emulate the USB socket. And here is the protocol, and we call it USB redirection protocol. And this protocol is trying to redirect the physical USB device into the virtual machine. And when it's enabled, and you can just redirect the visual USB socket into a Linux socket or Unix socket. So when you're trying to connect the Unix socket, you can just act as your plug or USB device into the USB guest machine. So that's the way we're doing this emulation. So let's see how we emulate the microcontroller and the firmware. So as I mentioned, the visual USB fuzzing framework is the project that inspired me to doing this work. So some of the code I just copied from that work, and we add some actual code to complete these simulation, and to make it work much better, and to apply it. And in our case, we have to switch the combination of VID and the PIDs in each fuzzing. So we just apply the run this code in a separate thread and then apply the new VID and the PIDs. So here's the result. We emulate the USB device and we test it, and it works for about 90 drivers. So this gives us a reasonable result to continue our research. So let's do some fuzzing. And here is just a schematic of the fuzzing system I designed. And on the above, you can see is VM pool. That's the place we place and store the each virtual machine of the USB drivers. And in the center, we can see it's just a main control unit. And we have in this unit, we have the VM manager. We have the every status monitors, and we also have the visual device managers. And and at the bottom, you can see there are driver pools that store our driver target we want to fuzzing. And on the right side is the storage to store the fuzz result, and we can use it for later analysis. And so let's go deep into this system. So let's talk about the VM management. And I divide the life cycle of VM into 3 stages. And the first stage is we're trying to involve the visual machine into from the initial state to the environment prepared, and then install the target driver in it. And after that, we take a snapshot of the visual machine to accelerate the fuzzing progress in the later. And so after that, we just initial to wake up the visual machine and plug our visual USB device, and then waiting for the visual USB to waiting for the target driver to be installed properly and is running. After that, we're doing the fuzzing and to monitor each the standards of the visual machine, and then we collect the results. So in this first stage, we prepare the environment for the fuzzing, and we also pre-install the target driver into the visual machine. And so in this stage, we have two tasks to achieve. And the first is execute the program inside the VM. And the second is collect as much as possible information for the target driver for the further analysis. So how to execute the program inside the VM? And we use the QGA, it's Cumulative Guest Agent. And it's just much like the VM tools, but you can customize it. You can add your own feature into it. And also expose some regular socket, and you can connect it in the host machine. So in this, by using this feature, we can achieve the read and write files, execute programs, and so on. And after that, we have to do some pre-install the driver into the OS, because if you're trying to plug your USB device into your host, and it takes quite a long time and to collect the drivers back from the remote server. So that's time consuming. We cannot, if we just using this progress, and we cannot control the actual time to achieve the fuzzing. So the best solution is to pre-install these drivers into the operating system, and then we can just speed up this progress. So in this when we trying to install the drivers, and we just collect some information of it, and about how many NF files was in it, and dynamically passing the NF file to detect the behavior when they trying to do the installation, and then collect the drivers they are actually doing during the installation. So, and here is just a workflow and how this installation analysis system work. So after in the second stage, we're trying to restore the VM from the snapshot and gets the USB a visual USB plugged in, and then make sure the target driver is running. In this stage, we have the two tasks, and the first task is launching the visual USB device, and then monitor the driver device status is if the driver is running properly. So first is, as I mentioned, is I just run the visual USB device in a separate thread and just connect it to the corresponding socket, and then after that is just waiting for the packets from the guest VM. And so here comes another task, and we have to monitor the device standards, and because if when the driver is running properly, and you can just access to this device. So we have to monitor the device standards, and here is just a little bit code for how to doing this monitor. So in the third stage, we're doing the actual fuzzing, and actually the entry point code fuzzing and the IRP handler fuzzing was occurred when just your initial in the second stage. So in this stage, we want to initialize the L control code fuzzing. So and here is just some task we want to achieve, and here's the L control code fuzzing. And we want to design. We have to design a fuzzer to run inside the VM and enumerate each L control code and do some random fuzzing. And also we need to record some buffer out data when the fuzzing, and that may result into some information leak or kernel mode. So here is just summarized, just a little bit of code snap of how I do the fuzzing. The fuzzer was written in in Python, and the core fuzzing unit is written in C++, C language, and compiled to the native binary, and that gives us speed up the fuzzing process. So after that, we have to monitor the various standards of when doing the fuzzing, and we just collect the process file and monitor and record the process and monitor every standards of the VM, and then just do it. And then after we got some BSODs or some crashes, we have to copy out the crash dump and the corresponding test case out of the VM. And after that, we can just save it for the later analysis. And after that, we restore the VM back to the snapshot and reapply the process file to continue the fuzzing. So that's just some trivial work to do. So here we come the result. And as this is just the first demo for how the system work. And in this demo, I'm trying to demonstrate and how I collect how the system work and how they cost the BSOD. So as you can see, is trying to just a bit. It's moving, and you can see it's just it's trying to install the drivers, and it's just showing the some that's indicated the drivers is running, and then the system start fuzzing, and after a bit you can see BSOD, one of the virtual machine shows BSOD, and the second, third virtual machine just crashed, and after that, and the system starts to collect the crash information of each virtual machine, and then that's it. So let's move on. So after we got all the fuzzing result, we have to get some reasonable result because there's quite a lot of crashes, and we have to do some automatic analysis on all of this result. So we have to first we have to reproduce the bug, because not all the bugs is reproducible. So we have to reproduce. So for this purpose, I designed a system for the bug verification system, and because our fuzzing system is running on the Linux to enable the kernel KVM, so we cannot port this system into the Windows host, so we have to launch 2 VMs to do the kernel debugging. And we launch 2 VMs, and the first is for the debugger, and the other is for the debuggee. And we redirect the 0 port to host the TCP/IP port, and just to connect to these 2 virtual machines together, and to do the kernel debugging on a Linux host. And it's really slow, and it takes time to debug to find a vulnerability, the root cause of vulnerability. But this is the only solution we can. And so after that, we have to do some crash dump auto analysis, because there's hundreds of the crash dumps. We cannot just drag the crash dump into the WinDebug and to see to wait for the analysis, and then we got the results. It's quite time-consuming and tedious. So I wrote just a bit script to accelerate this progress, and then it's really easy to write the code. So after that, we got all the crash dump be analyzed. So after that, we have to do some because it's a lot of bugs in the drivers. We have to locate the exact location of the bugs in the binaries. So but it's quite a lot, tens of the drivers needs to be analysis. So it's also time consuming. And then in this case, I wrote a plugin to just make life easier. So here is just a comparison of the before and you after apply the plugin. So if you have any experience on analyze the Windows driver framework drivers, you will find that when you load it into IDA, and there won't be any symbols and to indicate how many which APIs they are using and how many APIs they are using. So in this case, I just you can see just crapped on the left side, and I wrote an IDA plugin, and then we got reasonable results, and to recover the API names and every structures and every definition of each structures. So that's make the code, very readable. So here is just an example I found during the I/O control fuzzing, and as you can see, it's trying to call the address that stores in the RAX register. So it leads to the code execution in the kernel mode. So here's the result, and we submit all the bugs to the CVE request, and finally we got about 112 CVE IDs of all of these bugs. And I also submit all this stuff to Microsoft, and it has been 3 months past. They haven't finished analyzed each bugs, so I still have to wait. So, and all the previous pages is talking about how the bug discovery. So here is just the second demo, and I'm trying to exploit one of the bugs I found during this fuzzing. And in these demos, we're trying to exploit the bugs and then just bypass the authentication of the Windows lock screen. So let's see. So the researcher just trying to random typing on this to unlock the Windows, but obviously it's well failed. And then this is just tiny device I made it, and trying to plug into the USB socket and on it, and wait for the shellcode to be executed in some way, and then we have to wait for a bit. Yep, just a little bit, and then trying to do another random typing for the word, and to trying to unlock the screen, and it's did. Okay, so we come to the summary, and we found a novel attack service of Windows, and we established a whole working fuzzing system to discover the bugs, and we found the third-party driver developers differed in the code qualities. So it's introduced a lot of bugs, even the stack overflow and heap overflow and some non-pointer reference. So yeah, but Microsoft assigned it, so it's just the Microsoft fault, right? So okay, so yeah, and we will also find some way to do the fuzzing without any hardware. So to the end, I have to thank my leader, TKU, to support my research on this topic, and finally I also got a lot of results of it. And also, you can in the demo too, and the guy is Wenqun Wang, and he just doing all the exploit and make the videos. So thank you for your attention.